Today we are discussing about the oxidation reaction of aldehydes and ketones. And second topic, the reduction of aldehydes and ketones. So we move on to the first topic, that is oxidation by mild oxidizing agent. We know aldehydes are readily oxidized by mild oxidizing agents, while ketones are not. Here the mild oxidizing agents are: first one with the tolerance reagent, second one filling solution, and the third one Benedict's reagent, and the fourth one is with bromine water. Oxidation by tolerance reagent. A tolerance reagent is ammoniacal silver solution of silver nitrate, and it is prepared by dissolving silver nitrate in water by adding a NaOH solution and then adding aqueous ammonia. By using tolerance reagent, we can oxidize both the aliphatic and aromatic aldehyde. Now we move on to the reaction. When aldehyde RCHO react with the tolerance reagent is represented as AgNH3 twice plus. When aldehyde undergo oxidation with tolerance reagent, aldehyde undergo oxidation and it will change to the corresponding carboxylate anion or carboxylic acid, and the tolerance reagent will be reduced to the metallic silver, and this metallic silver will appear as a silver mirror on the walls of the test tube. Under ordinary condition, ketones will not undergo oxidation with the tolerance reagent. So, this is a test to distinguish aldehydes and ketones. Look at the example. When acetaldehyde is treated with tolerance reagent, we get the corresponding acetate ion and silver mirror. Likewise, benzaldehyde when treated with tolerance reagent, we get benzoate ion, and this tolerance reagent is reduced as metallic silver. Another important point regarding the tolerance reagent is that the tolerance reagent is used for selective oxidation of aldehyde. Look at the example of 4-hydroxycyclohexene carbaldehyde. When it is treated with the tolerance reagent, only the aldehyde part is oxidized, not the alcohol part. Another example, butylenol or crotaldehyde when treated with tolerance reagent, it will oxidize into butyenoic ion or protonate ion, and the oxidation will not affect the double bond. Oxidation with the second mild oxidizing agent, filling solution. Filling solution is an alkaline solution of cupric ion complexed with tartarate ions, and its solution is prepared by mixing copper sulfate solution, that is filling A, with alkaline solution of sodium potassium tartrate or Rochelle salt, that is filling B. Rochelle salt is also called filling B, or simply telling, it is prepared by mixing filling A and filling B. By using filling solution only, aliphatic aldehyde can be oxidized into the corresponding carboxylic anion or carboxylic acid. So, this is a test used to distinguish between aliphatic aldehydes and aromatic aldehydes. On oxidation with filling reagent, aliphatic aldehyde oxidized into the corresponding carboxylate anion, and the filling reagent reduced to red-brown precipitate of cuprous oxide. That means RCHO aldehyde, when treated with the filling reagent Cu2 plus, the aldehyde will undergo oxidation and will give the carboxylate ion, the corresponding carboxylate ion, and the Cu2 plus is reduced into Cu2O, cuprous oxide. Look at the example of acetaldehyde. When treated with Felling's reagent, it will give the acetate ion, while benzaldehyde, when treated with Felling's solution, there is no precipitation of red-brown Cu2O. That is, there is no reaction, no product is formed when aromatic aldehyde is treated with Felling's solution. So this is an important test to distinguish the aliphatic and aromatic aldehyde. Ketone also will not answer this test. Now, the oxidation with Benedict's solution. Benedict's solution or the Benedict's reagent is an alkaline solution of cupric ion complexed with the citrate ion, while the filling solution are complexed with the tartarate. Here the Benedict's reagent is complexed with the citrate ion. It is prepared from crystalline copper sulfur, sodium citrate and sodium carbonate. When aldehyde is treated with Benedict's reagent, aldehyde will oxidize to corresponding carboxylate anion, and Benedict's reagent is reduced to red-brown precipitate of cuprous oxide. By this method, we can oxidize only the aliphatic aldehyde. So, this is also an important test to distinguish between the aliphatic aldehyde and aromatic aldehyde. Only aliphatic aldehyde will answer the Benedict's reagent test. See the reaction of aldehyde when treated with Benedict's reagent. It will undergo oxidation and the aldehyde will give the corresponding carboxylate ion, and the Benedict's reagent Cu2 plus is reduced to Cu2O, and the ketone will not answer this test. So this is another test to distinguish between aldehydes and ketone. When acetone is treated with the Benedict solution, there is no precipitation of red-brown Cu2O. Now the fourth one, oxidation with bromine water. Aldehydes can be oxidized even with the bromine water. In this reaction, aldehyde will oxidize into the corresponding carboxylate acid, and during this reaction there is decolorization of bromine water occur, and the bromine water is reduced to hydrogen bromide. See the reaction between aldehyde and the bromine water. We get the corresponding carboxylic acid. Ketone will not answer this test, so this reaction can be used to distinguish between aldehydes and ketone. In short, by all these mild oxidants, we can distinguish aldehydes and ketones. By using Felling's reagent and Benedict's reagent, we can also distinguish the aldehydes, that is the aliphatic aldehyde and aromatic aldehyde. Only the aliphatic aldehyde will answer these tests. Now the second topic of this section, that is reduction reaction. Only two types of reduction reaction are discussing here. First one is reduction of aldehyde and ketone into alkyne, that is reduction of carbonyl group into methylene group. Second one, reduction of aldehyde and ketone into alcohol. First topic is the reduction of the carbonyl group to methylene group. Out of that, there are two types of reduction reaction: Clemmensen reduction and the Wolff-Kirschner reaction. First, we discuss about the Clemmensen reduction reaction. Clemmensen reduction reaction. It is a reduction of aldehydes and ketone into alkane using zinc amalgam and concentrated HCl. In this, carbonyl group is reduced to methylene and the corresponding hydrocarbon is obtained. This reaction is called Clemmensen reduction reaction. That is, when aldehyde and ketone is reduced with zinc amalgam and concentrated HCl, we will get alkane, and that type of reduction reaction is Clemmensen reduction reaction. See the examples. When propanol is treated with zinc amalgam on heating, we will get propane. When benzaldehyde is treated with zinc amalgam and the concentrated HCl on heating, we will get toluene. When butanol is treated with zinc amalgam and on heating, we will get butane. Wolff-Kirschner reaction. By this reaction also, aldehydes and ketone reduce into alkane, but here the reducing agent is different. When aldehydes and ketone is heated with hydrazine, NH2 and ketones at 140 degree to 200 degrees Celsius in presence of diethylene glycol or DEG or dimethyl sulfoxide DMSO, the carbonyl group is reduced to methylene group and the corresponding hydrocarbon is obtained. This type of reduction reaction is called Wolff-Kirschner reaction. See the reaction of aldehyde or ketone with hydrazine H2N NH2. It will reduce into hydrocarbon. See the acetaldehyde when it is treated with hydrazine in presence of ketones and it is heated, we get the corresponding ethane. When benzaldehyde is treated with hydrazine in presence of ketones and it is heated, we get the toluene. When acetone is treated with hydrazine in presence of ketones, we get propane. When acetophenone is treated with ketones, we get ethyl benzene. So keep it in mind, the reducing agents that is used for the reduction. In Clemmensen reduction reaction, we will use zinc amalgam and concentrated HCl, whereas in Wolff-Kirschner reaction, we will use ketones and hydrazine at 140 to 200 degrees Celsius in presence of DEG or DMSO. Now the second reduction reaction of aldehydes and ketone into alcohol. We know primary alcohol on oxidation will give aldehyde. That means aldehydes on reduction will give primary alcohol and ketone will give secondary alcohol. So first one is catalytic reduction. It is the reduction by using hydrogen in presence of catalyst like nickel, palladium or platinum, etc. that will convert aldehyde and ketone into the corresponding alcohol. Here aldehydes are reduced into primary alcohol and ketone will to secondary alcohol. See the reaction. When aldehyde is treated with hydrogen in presence of catalyst like nickel, platinum or palladium, we will get primary alcohol, while ketone will give secondary alcohol. See the reactions of aldehyde, acetaldehyde when it is treated with hydrogen in presence of catalysts like nickel, platinum, palladium, we will get the primary alcohol, that is ethyl alcohol. Whereas when acetone, the ketone, is treated with hydrogen and in presence of catalysts like nickel, platinum, palladium, we will get secondary alcohol. Here we get isopropyl alcohol. When benzaldehyde is treated with hydrogen in presence of these catalysts, nickel, platinum, palladium, we will get benzyl alcohol, that is primary alcohol. When acetophenone is treated, we will get 1-phenyl ethanol, that is secondary alcohol. When cyclopentanone is treated, we will get cyclopentanol. Reduction using metal hydrates. Reaction of aldehyde or ketone with sodium borohydride or lithium aluminum hydride followed by water or some other proton source yields an alcohol. Aldehydes are reduced into primary alcohols and ketones are reduced into secondary alcohol. This reaction involved irreversible nucleophilic addition of hydride ion at the carbonyl carbon. See the reaction when aldehyde is treated with lithium aluminum hydride or with sodium borohydride, we will get primary alcohol. When ketone is treated, we will get secondary alcohol. Another point is that if double or triple bond is in conjugation with carbonyl group, lithium aluminum hydride will reduce with the double bond or triple bond, but sodium borohydride will not. See the reaction when butyl is reduced in presence of lithium aluminum hydride, we will get butane 1-ol. That is, the double bond is reduced to single bond. When this butyl is reduced in presence of sodium borohydride, we will get but 2 in 1-ol. Mechanism. The key step in the reduction of carbonyl compound either by lithium aluminum hydride or with the sodium borohydride is a transfer of hydride ion from the metal to the carbonyl carbon. In this transfer, hydride ion act as a nucleophile. The metal hydride reagent delivers the nucleophile hydride ion which attack the carbonyl group to form tetrahedral alkoxide. After this, the alkoxide is protonated upon acidic hydrolysis to form an alcohol, and aldehyde will reduce into primary alcohol and ketone will reduce into secondary alcohol.